I'll pass, and I'll approve it. Okay. Oh. Why is this not loading? All right, if I can get your attention up front, today we are talking about combining functions to create new functions. And there are two ways that we can do that. We can combine functions algebraically, addition, subtraction, multiplication, division, or we can make a composition of functions. And we're going to start with the algebraic stuff, because that goes a little faster. We use shorthand as mathematicians when we indicate that you're doing something with two functions. So if I'm adding two functions, f of x plus g of x, sometimes you will see it written as f plus g of x. They're indicating the operation that we're performing on the names of the functions. Any guess what f of x minus g of x will look like? F minus g, yeah. F minus g. And you'll see especially lazy mathematicians just write the f minus g and drop the of x. Yeah. Good. So f of x times g of x is often just fg of x, because we know when we have two variables or two letters next to each other, that is implied multiplication. And then very good. And sometimes you'll see it as a slash. More often, they'll actually write it with fraction notation and build the fraction, f over g. Yeah. Good.
So there's 3 ways to show division?
There are 3 ways to show division. This is going to be the one that's most common, because this is the one that your book prefers and most mathematicians will use. I don't know why I'm throwing my words today. Okay, so let's do some examples. I'm going to do some. You're going to do some for practice because it's good for you. For example 1, they ask us to find and simplify the functions g minus f and g divided by f, given that f of x is x minus 1 and g of x is x squared minus 1. So we're going to go ahead and start with g minus f. And it is what we think it is. I am going to take the function for g, and then I'm going to subtract the function for f. I just need to substitute in what f and g are. The first function is g, so I'm going to copy g. G is x squared minus 1. Right? That's the guy that's in front. The guy behind the subtraction is f. I'm going to copy f. F was x minus 1. Yeah, f minus g. And then I simplify. And my instinct says, hey, let's distribute the negative sign through the parentheses behind it. So my first function, x squared minus 1, just hangs out. A negative 1 times an x becomes a negative x. And a negative 1 times a negative 1 becomes a positive 1. Yeah. There's one more thing I can do. How can I simplify that? Very good. Combine those like terms, those constants. Perfect. And plus 1 minus 1 is 0. Yeah, they're going to cancel. So I'm going to be left with an x squared minus an x. Yeah, hopefully. Yeah, good. Very good. So addition and subtraction, you may need to distribute the subtraction sign if you're subtracting, but then it's just grouping like terms. Constants with constants, x's with x's, x squareds with x squareds, group your like terms. Good. And that's next. G over f means division. So I'm going to set up my fraction. G is my numerator, f is my denominator. So g on top F is on bottom. That can be simplified. Question is how? What can I do to simplify that? So tempting. -1 on top, -1 on bottom to cancel. I am not allowed to cancel things when they are being added or subtracted. Those are terms. I cannot cancel terms. I can only cancel stuff that's being multiplied. I can only cancel factors, meaning I have to factor the top before I could cancel stuff. Everybody's favorite math F word, factor. That's a pattern on top. That's very common. Perfect square minus perfect square, that's a difference of squares. That's a factoring pattern that if you don't remember, we're going to become very familiar with soon because our next unit is on polynomials. And I know that's going to factor into x plus 1 times x minus 1. Now what can I do? Cancel those terms or those factors, x minus 1, x minus 1. Good. So what am I left with? X plus 1. Happy face. So when we're doing this, we're going to have to pull from lots of different tool sets, right? I have to combine like terms. I have to be able to factor and cancel. Sometimes I'm going to have to make common denominators if I'm adding or subtracting rational functions. We're going to talk about those in our next unit. But all of those algebra skills that we've learned in Math 1 through Math 3 are used to simplify the expression. Yes? Minus 1? Oh, so the x squared minus 1, if I were to take what I had here, so what I factored that into was x plus 1, x minus 1. If I FOIL that back out, x times x is x squared. Yeah? X and minus 1 are minus x. X and plus 1 are plus x. And plus 1 times minus 1 is minus. And you'll notice those guys, we get back to x squared minus 1. So it's there, it's just hidden. Yeah. Yeah. Good question. Other questions? There's a chance to pick my brain before I ask you to try it. Other questions? No other questions. Okay, then I'm going to ask you to do a similar thing for example 2. I'll have a couple minutes on the clock. I want you to find f times g and f plus g. F times g and f plus g. Maybe a couple minutes. All right, everyone. We're going to come back together. We're going to start with f plus g. Can I get a show of hands who wants to boss me around to tell me how to do f plus g? Brownie. Luis, can you help me? Yeah, how do I do f plus g? What should I do? X minus 1. Combine the like terms. Okay. So what would my answer look like? I see some nodding. Do we agree? Very good. Very good. I agree. That is perfectly correct. If you were an experienced mathematician, you would write it in a different order. Very good. Yeah. Typically, when we write polynomials, biggest exponent first and then in decreasing order. But it's not that your answer was incorrect. Just as we start working with polynomials in our next unit, having the leading term with the biggest exponent in front makes it easier to work with. Good. Very good. Snaps to the. Yeah. Okay. Who wants to boss me around for the next one? F times G. Everybody's all quiet. Frowny face. Gabriel, what should I do? That's all you got. So what are we doing with x squared minus 1 and x minus 1? Multiplying them. Yeah. When I'm multiplying, does it order the matter I put those things in? No. For multiplication, it doesn't matter that G's in front of F. Good. So those are what we call binomials. They have two terms each. When I multiply binomials, I have two choices. I can FOIL, or I can use the box method. Do we have a preference? FOIL? That seems to be the popular one. So FOIL is first, outer, inner, last. Yeah, first, outer, inner, last. First, outer, inner, last. So first is x squared times x, which is x cubed. Good. Outer is x squared times minus 1, which is minus x squared. Inner is minus 1 times x, which is minus x. And last is minus 1 times minus 1, which is plus 1. Am I done? And I see, Good. I don't see any like terms up there. All of the x's have different exponents. There's only one constant. There's nothing else I can do. That's it. That is as pretty as it's going to get. Yeah, good. Very good. Okay, questions on how to combine functions algebraically? No, everybody looks like they're in a state of food coma. Okay. We'll talk about the other big idea for today, which is the other way to take two functions and make a new function, and that is through function composition. So a function composition is when we use one function as input for another function. So instead of taking a number and using it as input, instead of taking a constant like a or h and using it as input, I'm going to take a second function and input it into the first function. And when I simplify that, it gives me a brand new function, which is a composition of the other two. We can express a composite function using two different notations. My preference is f parentheses g parentheses x. So f of g of x. I like that notation because it is very clear that g is the input for the function f. The other way you will sometimes see that same idea written is f and then a little open circle and then g and then x, and it reads the same way, f of g of x. The outer function or first function forms the overall structure. The inner function becomes the input into that structure. To write a composite function, we substitute, big word I know how to spell, substitute the input function into the output function, and we simplify. We've heard those words paired together a lot over the last week or so, because it's the same way that we evaluate a single function. We substitute and simplify. The only difference is now the thing we're substituting in is a function instead of a number. The idea is the same. We're going to do some together, and then I will have you try some on your own. So it says, consider the functions f of x equals 2x plus 1 and g of x equals 3 minus x. Find f of g of x and g of f of x. So we will start with f of g of x. And here is how I do it. Remember that the outside function, the very first thing you see when you're reading from left to right, is the overall structure. So I am going to copy f down, and everywhere I see an x in the expression for x, or f, I'm going to put parentheses in place of the x. So f is 2 times something plus 1. That's what it says, 2 times x plus 1. That's 2 times something times 1. 2 times something plus 1. But now my input isn't x, it's g of x. The thing that goes in parentheses is g. G is 3 minus x. So where f had an x, now we have g in place of x. Once the substitution is done, it's just simplification. I know you guys know how to do that. If I wanted to simplify, what's the first thing I should do? Starts with a D. Distribute, yeah. Distribute that 2 through. 2 times 3 is 6. 2 times negative x is 2x. Jordan, what's my last step? Very good. Combine like terms. There's a constant in front, a constant in the back. So 6 plus 1 is 7. And I'm going to write this in a very particular order because I recognize that function structure. So f of g of x, our new function, is negative 2x plus 7. What shape will that make when I graph it? Alan, what shape will that make when I graph it? Y equals negative 2x plus 7. What shape? The first function you learned with me in Math 1. Linear, yeah, you do know. Very good, perfect. I was going to make a straight line. G was a straight line. F was a straight line. Their composition gave us a straight line. Not terribly surprising. Let's try the reverse. The next one says find g of f of x. G is the first function, g is the structure, f is the input. So I'm starting with g. G is 3 minus something. 3 minus x. And the thing that goes in the parentheses is no longer x, it's f of x. F is 2x plus 1. And then we simplify. Same process. Distribute the negative 1 through the parentheses. 3 minus 2x minus 1. And the same thing Jordan said, combine those like terms. 3 minus 1 is 2. Are those two functions the same? F of g of x, g of f of x, are the same? No, they're related. I see the same slope in both. They're both linear, they're both same slope. They've got different y-intercepts. When you have compositions of functions and you reverse the order of the composition, those resulting functions will be related. They will very rarely be the same. We have a special name for functions that give us the same result regardless of the order of the composition. Those types of functions are called commutative. So commutative functions mean that if I do f of g of x, I should get the same result as if I did g of f of x. Results would be the same. And you guys just told me that our last example was not commutative because negative 2x plus 7 is not the same thing as negative 2x plus 2. The results we got were different. So f and g for that example were not commutative. The order mattered. Okay, before I set you loose, on your example, does anyone have questions on what we just did? Yes. Oh, so remember that example 4 was talking about example 3. So I go back to example 3 and I look at what we just did. Here is f of g of x. Here is g of f of x. If the functions were commutative, those two things would be the same. And they're not. So this f function and this g function are not commutative. Yeah. That was a good question. Other questions? No. Okay. Example 5. I want you to do the same thing. Calculate them both ways. Decide if they're commutative. So f of g of x on one side, g of f of x on the other side. Do you get the same result? Yeah? I'm going to put a couple minutes on the clock. Work with your group mates. Tricky. Those were harder because those functions are more complicated. The process is the same. The process is the same. For f of g, I'm just going to write it as f of g. F is the function, g is the input. F is x squared, f of x is x squared plus 1. I'm not inputting x, I'm inputting g. This should be g squared plus 1. What is g? Square root of x plus 2. No x squared floating around anywhere. The x gets replaced with whatever g of x is. So I shouldn't have an x squared floating around loose unless g had an x squared floating around loose, because I am replacing x with whatever g of x is. And it's going to feel weird for a while. You're going to mess up. You're going to make boo-boos. That's why we're practicing, yeah? Be patient with yourself. Looking at that, what simplifies? Square, yeah. Squares undo square roots. Yeah, and I saw, after a little bit of time, that's starting to pop up on people's papers, which is exactly right. What are we stuck with, Bruno? Okay, you're good now? Okay. Next one was less pretty, but the idea is the same. If I could write. So we're doing g of f, meaning now my structure is g. G is square root of x plus 2, but now it's square root of f plus 2. And f is x squared plus 1. How can I simplify? If I were multiplying, yes. This is addition instead of multiplication. If I remove the parentheses, that might help. So that goes away because I don't really need them for addition. Like terms, yeah. There's a 1 and a 2 there. So square root x squared plus 3. Tempting to do that, yeah? Just like I can't cross cancel in fractions when there's an addition in between, I can't separate a square root if there's an addition in between. I can only separate roots when it's multiplication. That doesn't get any prettier. He stays. He's done. Which I know is uncomfortable because they don't look anything alike. But it's correct, yeah. Yeah. What time do we get out of this class? Okay. We'll do some more practice when I see you tomorrow for minimum day. We're going to finish these notes and then more practice with compositions. I want to make sure you got it down. Yeah, we've got time for that because the last thing on your notes is just more practice. Yeah, it's fine. I don't know. I haven't seen the schedule yet. When I see you on Thursday, we're going to do transformations of functions and then a Desmos graphing activity. A reminder, if you want to know when your midterms are, where is that information? We don't have Canvas yet. Not in the syllabus. There is a calendar thing posted in Google Classroom. It should say class calendar. It should be linked at the very top of the classwork page in Google Classroom. It has our midterm dates. It has what we covered on each day. Please monitor it. All of that will be in Canvas once everyone has access, but I have not been notified that you do yet. If you have questions after school today, I'll be here till 5.